Welcome to Coffee Break, the live stream series brought to you by Microchip Technology, where our mission is to educate, entertain, and empower you to innovate in your designs. I'm your host, Dana Curtis, and welcome to Season 14 of Coffee Break. As always, we're here to dive into the fascinating world of embedded control technologies, integrated circuits, and all things smart, connected, and secure in about the time it takes to enjoy a fresh cup of coffee. For those of you joining us for the first time, Coffee Break is a live broadcast, and we want you to participate. Before I introduce our special guests, let's take it over to Aliyah Fahout for some housekeeping items. Aliyah, what do you have for us?
Thanks, Dana, and hi everyone. Thank you for joining us today. We are currently live on YouTube, Facebook, and LinkedIn, and we invite you to participate in today's episode by leaving your questions and comments in the chat, or you can email us at livestream@microchip.com after this broadcast. If you're with us on YouTube, don't forget to subscribe to our channel and click the bell so you know when we're live and when our next episode is. If you're with us on LinkedIn, subscribe to the event so you can get all the information related to this episode. Back to you, Dana.
Thanks, Aliyah. Today we have two very special guests joining us. Bob Proctor is a technical application engineer, and Dylan Turner is a technical marketing engineer here at Microchip Technology. Welcome, Bob, Dylan. You guys are here to pose a unique question for our audience. And we say to ourselves, let's be logical. CPLD or CLB? So we've got our coffee ready. Let's start with the obvious question. Why programmable logic?
Yeah. So there are plenty of reasons why you would still use programmable logic today. And to start us off, fixed reaction time is a big one. Fixed reaction time because you're not really dealing with the same things you would deal with in hardware. There's no interrupt delays, and you have a path set in silicon. Parallel processing, which can be better and faster than CPU. Traditionally, when you are programming or doing anything with chips, you're going to be following a sequential instruction cycle. Parallel processing allows you to do multiple processes at once. On top of this, they're also super reliable due to the dedicated hardware I was talking about earlier. So not only do they have a path set in silicon, and then this will segue to my last point, but that dedicated hardware is a component or aspect that is independent from one another, So you could have multiple processes going on, and they would only interact if you want them to. Programmable logic spawned out of necessity. So on this slide, I actually have a basic addition circuit and a discrete logic IC. So these were very beginning circuits, and you've probably seen some of these gates in your intro to programming or intro to coding classes, but these are your ANDs, ORs, NORs, NANDs, and this one also has an XOR. So if you want to actually bring these circuits from schematic to real life, you'd have to implement them using ICs. And the problem with that is you'd never get the exact amount you'd want, so you're dealing with a lot of extra parts with a lot of room taken up, and on top of that too, if you messed up, you were forced to go out and buy a new one. Enter in CPLDs, you were no longer constrained to one part. You could have whatever you needed, or if something didn't work out for you, you could swap one out. And I'll let our expert, Bob, talk to us about CPLDs.
Okay, so let's bring it over to CPLDs, Bob. What can you tell us about CPLD?
So CPLDs are basically any sort of gate that you would want in an arrangement where you can connect them up in any number of ways. So in the picture on the slide, you can see the zoom in box. It shows basically a logic gate, a kind of a universal logic gate. You can program it to be any combination of simple logic gates. And you can enable or disable a latch to do different kinds of latching functions. And on the left side, the larger view, you can see that there's this large array, this grid of interconnections. So on the far left, there's all these input pins. Those are connected to wires in this matrix. And then on the right side, there's all these different macro cells or logic cells. And you can program the interconnection so that each macro cell can select from any of the number of inputs, as well as every macro cell can then feed back and become another wire in the matrix, so that you can cascade logic cells or macro cells into other macro cells for more complex functions. So in this sense, you can basically program it to be anything you wanted. And with the CPLD, you're programming it through EEPROM's memory cells, a non-volatile cell, where when you power it up, it's there. It's already programmed. It's ready to go. So you can be up and running in less than a microsecond. So the advantage there, of course, is the fact that when you turn it on, it's ready to go. It's fast.
Yep.
Another thing is the actual logic itself is fast. I mean, these are designed to be 100 megahertz or more. You can have simpler ones, like 8 macrocells. You can have much more complex ones. In this case, the CPLDs go up to 128 macrocells.
Quite a range.
So you can imagine all the different things you can put in. When you have that much space, you can have many parallel things going on. You can have, in one side of it, you can have a multiplexer going on where several inputs will select an output. You can have a counter going on that is pacing or setting a state machine for the system. Another part of it, you can have a PWM going on where it takes a value from the counter and compares that digitally with another number and produces a variable pulse width output. So you can program all kinds of things, as well as arithmetic functions or whatever. So in that sense, they're very universal and can be applied anywhere. From the previous slide, we saw that there was that proto board with all the wiring on it.
Right.
Basically, you suck all those chips up and all the wiring inside the CPLD, so your board is cleaner. You can lay out everything in one layer, and it goes straight in, and then you can just rewire it inside the chip. And so it does make your circuit simpler. And because it's all sucked up inside the chip, again, you get that added reliability and speed. Imagine doing that proto board, and how many of those wires that you plugged into the proto board don't have good connectivity?
Right.
So
Right.
talk about reliability. You really got to have something that removes all these variables from the system, and
Right.
CPLD is really good at that. Now the CPLD products have been around a while. They were designed for 3.3 volt circuits and 5 volt circuits, and none of the ones that we have any sort of analog in them. So you can't really interface. When I say multiplexers, you're not going to be using it as an analog signal multiplexer to bring a variable voltage. It's a digital multiplexer in this case. But if you want to have connectivity to an analog circuit, like through a comparator, an ADC, or a DAC, you'd probably have to hook that up externally. And so that kind of gets us into other options that may be able to interface analog and digital together.
Okay, so that's a good breakdown of CPLD. What about CLBs?
Yeah, so we're still under this umbrella of programmable logic, but while the CPLD is a specific part that has real-life components, this is a peripheral within our microcontroller. Not saying that it doesn't still have real-life components, it still does. This is a brand new peripheral on our brand new part with a brand new family. A lot of brand news.
Yeah, they're new.
So this is with our brand new family, the PIC16131 family.
Okay.
And so this peripheral, like other peripherals, is highly integrated. So you can use this with a combination of those analog blocks that Bob was talking about earlier that you don't really necessarily get on the CPLD. Versus CLB, you could have an auto set conversion timer for your ADC. You could have your clock sources synced up to your one timer. Mm-hmm. You have plenty of options for it. Since it's also a peripheral, it can operate in sleep, and it does operate independently of the MCU. So you kind of get that hardware logic sort of vibe from it.
Okay.
This is lookup table based, so Bob was mentioning earlier that they use macrocells. So this is lookup tables, and these are basic logic elements. Amongst the entire family, we only have 32, but on the bottom of this slide, we have a diagram that shows the LUT going into a D flip-flop and a MUX. These are the basic compositions of all our basic logic elements. And more specifically, a LUT, and that's what our logic is based off of, this lets you control what I was mentioning earlier, those AND, ORs, NORs, NANDs, but it gives you an opportunity to make your own sort of logic. So if you wanted all inputs to be high in order for a true, you could have that. If you want them all to be low, or if you just want just C active, you can also have that. This is also nice too, because as I was mentioning, this is hardware logic. You can operate this with the system clock or asynchronously with one of our timers or an external clock up to 100 megahertz. There are plenty of advantages to use a CLB over a CPLD. For one, a wide voltage range. So even though we are hardware logic with a microcontroller. So we get that added bonus of that 1.8 to the 5.5 volt range. We have an integrated on-chip analog. So as I was mentioning earlier, these are our DACs, our ADCs, our integrated op amps, and our comparators as well. So we have plenty of peripherals that you can already use with this peripheral as well, and it will help save you some time. We have an excellent logic to cost ratio, and what that means is we have 32 BLEs amongst the entire family, but you could be, I should mention, you have 32 BLEs for the entire family, but that's all under that dollar price point.
Right.
When you're looking against other things in the market, you could be paying a lot more for a lot less. Some CPLDs only have 10 macro cells, for instance, and in the future we hope to add more BLEs to this. And on top of all those, also low power consumption. Since this is a peripheral, you can turn it off at any time. You can only use what you want to use. And with all those in mind, we also have a brand new tool that we're using with this, and this is a CLB synthesizer. And this is our brand new tool that lets you get access to this hardware logic. We have it already on our website if you do www.microchip.com/CLB, or you can also check it out on MCC Melody. But important thing to note is we try to get the best of both worlds when it comes to hardware logic and microcontrollers, but we do have some limitations, albeit the limited density. Even though we are at a good price point for it, you still can get more when you're looking at CPLDs, which can get up to a max of 128 macro cells.
That's about the same.
Right. Or even FPGAs, which can go up to the 1000s. And another limitation being we're a small package size, which is nice in a few cases. But if you did want more inputs and outputs, that would be Bob's market.
Well, it's not that we have choice, right? So you rattled up 3 instances right there where you've got various options for the designer to go to. Is there a use case that would kind of allow for an easy compare and contrast between the two?
Yeah. So on this slide, we have a solar panel inverter.
Okay.
So a solar panel inverter converts AC into DC power, and it does so using a PWM control frequency. This control frequency has to be monitored with some sort of safety net or like just watcher, and it's poor practice to do this in software. So it's way better to do something like CPLDs or CLBs with that hardware logic. You get that fast response time. I'm going to let Bob talk more on when to use a CLB versus a CPLD.
Okay, so this is an interesting case. So on the left side, or in this case, the middle of the slide, we show microinverters, right? So imagine at your house, you've got solar panels on your roof. The solar panels are probably going to be anywhere from 300 to 500 watts each. And so you can have a system that uses microinverters. So every solar panel has a little inverter on the back, which converts the DC from the panel into AC, like 240 volt AC. And that 240 volt AC is then paralleled with all the other panels and microinverters. That's fed into a meter, and that's fed into the grid so that the utility can then credit you for the power that you're generating and selling to the grid. So it's because the panel is probably less than 500 watts, the microinverter itself is about 500 watts. It means that the electronics, the passives, the inductors, capacitors, everything else in that box, in the back of the inverter, is going to be fairly small. And so in that sort of situation, if you looked at like what are the worst case conditions that can show up, probably the worst case condition would be something happened where there was a short circuit on the output. Now, with your grid, you've got breakers, you've got fuses, you've got other things that are going to protect the grid. You're not going to hurt the grid. It's just going to pop a breaker or whatever. But for the microinverter, this tiny little 500 watt circuit, it could easily blow up its transistors and take out a whole string. So to prevent that, you need to have some mechanism that can, you're generating PWM, which is like boosting the voltage, and then you have another set of PWMs, which are inverting it, that is, say, doing the AC conversion. All of those have to stop, like, immediately. So in that case, it's nice to have some sort of gating mechanism, something that intercedes between the PWM output, the timer output on the microcontroller, and the gate drives of the FETs or IGBTs that you're using for the inverters. And that's where programmable logic can come in, that it can be very fast in order to take the overcurrent signal and shut down everything. Your processor may still be thinking about it, may still be processing an interrupt, may take a few microseconds to react and go, oh, we have a fault. I'm going to send out a message, I'm going to shut down everything, I'm going to turn on a light, I'm going to activate a signal on Bluetooth, whatever it has to do, it's going to indicate a fault. But it's hard for the microcontroller itself to intercede and shut down everything all at once. That's where that logic gate can come in and boom, just shut down everything. Now for the microinverter, again, it's a 500 watt circuit or so. You can probably get away with shutting it down within a microsecond or two. 500 watts means that the components aren't very big. The total power available isn't very much. The panel itself is a power source and not really a low impedance, huge reservoir of energy. And so you may be able to use a CLB there to shut down, I mean, you use several of them, obviously, but you use several of them to shut down the PWM signal outputs from one trigger signal. Now, the other thing that could happen would be over voltage conditions. So that would be if the output load suddenly went open, the voltage may rise very rapidly because you still have energy in the conversion process and stored in the inductors and things. And so in that case, you still have to have some way of mechanism to shutting it down fast, maybe even to clamp the voltage. But probably with a microinverter, you can get away with that, do that pretty easily with CLBs. Now on the right side, we show what we call a string inverter. This is actually more common in homes, at least in my neighborhood. What I see is that there's one large box on the side of the house. It's near the power meter. And there they're taking all the solar panels on the roof. And in this case, they're wired in series parallel, and they're probably going to add up anywhere from 10,000, 12,000, 15,000 watts. That's a lot of energy. That's a lot more than 500 watts. And that's going into one large inverter. It's doing the same basic job. It's taking that DC power, converting it to AC, so that then the utility can give you credit for what you pump into the grid. But the inverter itself is made up of larger components, larger transistor arrays, larger inductors and capacitors. It has to take these PWM square wave signals and turn it into fairly clean sine wave. So there are a lot of these passive components in there. When it comes to high power circuitry though, it's interesting that because it has to be higher voltage, there's higher, the inductance tends to be smaller, even though inductors themselves are larger, the time constants get very fast. So in this case, if we imagine there's a short circuit condition, probably a microsecond isn't going to be good enough. In fact, you might want to be down to the nanoseconds. So the same idea with the microinverter applies to the string inverter, except you just got to be faster. And so you probably, in this case, you can use, I mean, you might even have more PWM signals, right? But you're still going to need to shut them down fast. And so a CPLD can be very handy there to take the signal from the overcurrent sensor or over voltage sensor and string it through there and shut down all the PWMs, well under a microsecond, so that you're preserving your circuitry, your traces don't get burned up, your transistors don't start on fire, everything is protected, and then you can recover from the fault. Whatever that caused the problem can be fixed, and then it can come back online without destroying everything. So this is, this basic example kind of shows that in a higher power circuit, you kind of need higher speed. A lower power circuit, you still need good speed, may still have to be faster than a microcontroller interrupt, but a CLB may be ideal for that. So that's kind of a good example there. And of course, for the higher power circuit, the current consumption of the device may not be such an issue.
Right.
Yeah, but it's probably an oversimplification to suggest that current is how you decide between the two components, right? Is there, where do these two intersect?
Yeah. So we made a little Venn diagram to kind of summarize all this information.
Okay.
So when you're focusing on CPLDs, this is going to be your faster market, your faster boot up time, your bigger packages. So you're going to have the more IOs. With bigger packages, more macro cells, for instance. So you're not with 32, you're with 128. And also, importantly, too, configuration is retained and power off. And so plenty of reasons why you would go for a CPLD. When you're going with the CLB, it's important to note too that you get an added benefit of an MCU. So you have the low power consumption that comes from our peripherals. You only power what you use versus a CPLD, which would power every macro cell even when not in use. Which would be more important for like battery operating devices, which a CLB would be more perfect for than a CPLD. Or
Yeah, I haven't actually seen too many battery-powered circuits using CPLDs. That's really not normal.
So it'd be a niche market. And on top of that, you have integrated analog and digital peripherals. So like Bob was mentioning earlier, you're missing some analog components when you are in CPLDs, but with the CLB, you get the added peripherals that come along with most of our MCUs already there. Small package size, so if you're trying to clear up or save some space, this is perfect for that. It's also perfect for your more glue logic because it is that smaller package size, the smaller BLE size. This is LUT-based architecture, so it's the same but a different level of configurability. And on top of the, like I was saying earlier, you're working with hardware logic with a microcontroller, so you get that 1.8 to 5.5 volt range. And on top of the 32 BLEs you also get the additional MCU core, so that allows you to free up your space to do more. But it's important to note that this is all under the umbrella term of hardware logic. So that means you get your dedicated hardware, your reliability of hardware execution, predictable timing, and parallel processing that comes with most of these devices.
Now, one of the things that seems intriguing to me is the fact that with the CPLD, we remove a lot of the circuitry from the board, remove a lot of the wiring. The CLB does that one step further because now you can interface to your other peripherals inside the chip and go to your logic device from a UART, from a PWM, from a timer, and you can do added manipulation to those signals that are already either coming to or from a peripheral. To me, it's a wonderful idea.
So I'm getting the sense that like a lot of things in the Microchip's product portfolio, you've got choice, right? You've got CLBs, you've got CPLDs, you've got FPGAs, but I also see with that intersection there that you have a path to scale. So if somebody doesn't quite know what they need, they've got options to go from one to another also to grow their applications. That sound right?
Right?
Yeah.
Well, where can we learn more, I guess is the next logical question.
Yeah, so we have plenty of resources that make hardware logic easy. If you want to learn more, we have www.microchip.com/programmable logic. Make sure to bookmark this page because we do have a webinar following November 14th.
Okay,
and
November
we
14th.
will also have another live stream later in January.
Okay.
If you want more specific CLB resources, also, again, make sure to click the top link at www.microchip.com/programmable logic. We will summarize everything we've talked about here, and we will give resources to both CLB and CPLD. That link, more specifically, will have a link to the CLB synthesizer and also the PIC16131C Nano. So,
Which is what we're looking at on the right here?
yes, it's going to be in the top right corner. Okay. This is going to be the beginner hardware. If you want to get used to CLB today, you can order this and already get started on the CLB synthesizer. If you want more specifically CLB resources, we have CLB code examples at discover.microchip.com. Just make sure to search CLB. If you want to try this on live hardware, we have try.microchip.com, and we have a neat little CLB demo that involves traffic lights, and you get to see how logic actually flows within diagrams like these.
Okay.
If you want to check out CPLD resources,
Yeah, there's a tool online you can download. It's called WinCouple, right? So Couple is a hardware design language, and WinCouple is a free tool that lets you start doing Boolean logic configurations for a CPLD, SPLD, simple programmable logic. And what's cool about it, we have, when you install the software, there's a bunch of examples. And really, that's one of the best ways to learn it, is just look at the examples. Or you can just download the example file as a zip file separately. But that is the basic, simplest way to get programming in CPLDs.
It's important to note too, all these resources are free, except for the Curiosity Nano. You will still have to buy that from us.
Okay, but they're all on our website, right?
Yes.
Yep.
So with that, let's get over to Aaliyah to see what kinds of questions we're getting from the interwebs. Aaliyah?
Thanks, Dana. We have a question from Adrian coming from YouTube. Is the CPLD and CLB reprogrammable during program execution in the microcontroller?
Interesting.
Yeah.
I can tell you the CPLD, once it's programmed, it can be reprogrammed, but not in circuit, or not live.
Mm-hmm.
So with a CPLD, some of them, the smaller ones, need to be unplugged and stuck into a parallel programmer, and other ones can be programmed through a JTAG interface, but it's not the sort of thing you're going to do live.
Mm-hmm. I am aware that you can do in serial circuit programming with the CLB, and I'm pretty sure, but I will have to get back to this, or even have this question forwarded to our email.
Okay.
But I'm pretty sure you are able to do a live change of the bit stream with CLB.
Okay. All right.
Thank you both. The next question I have for you is another link, or this is a LinkedIn question. What does excellent logic to cost ratio mean?
Yeah, that's a great question. So excellent logic to cost ratio means a very baseline. We have 32 BLEs. We are under $1 when it comes to price point. When you look at other things like CPLDs, for instance, you could be paying $4 for, again, only 10 macro cells. And with FPGAs, that's not even a price point worth talking about, because you're getting to like the 10s or the 8s, you know, and it's just incomparable here. But on top of the 32 BLEs, one thing to also consider is you also have that included MCU core. So you have that sort of bonus logic with it.
It's one thing that's characteristic of Microchip is we pack a lot into a single item, so there's extraordinary value there.
Completely true.
Great, thank you. Last question for you today is coming from Gurpreet Singh on YouTube. What is the difference between FPGA and CPLD?
Okay, FPGAs, field programmable gate arrays, are basically the same idea of a CPLD, except much larger. Most FPGAs use a lookup table, and that lookup table is stored in SRAM cells scattered throughout the FPGA. So all the various logic and gating arrangements are programmed in at power up. So if you write code in Verilog or VHDL or schematic capture or something like that, which sets up the circuitry inside an FPGA, you compile that, and it goes into an external EEPROM. And that external EEPROM is connected through SPI or I2C to the FPGA, and when it powers up, it detects the EEPROM and unloads the data and fills up its array of all its configuration bits from the EEPROM, and that then is your FPGA program. Now, the FPGA itself is going to be bigger. It's not going to be limited to 128 macrocells. They'll probably start there and go to thousands or even millions, depending how big you go. And so with an FPGA, you can actually drop in a software coded version of a microcontroller core. You can put in lots of different fancy peripherals. Many people use FPGAs for digital signal processing. So they want to design a filter, but they want to have the filter reconfigurable. And so they design it into an FPGA so that they can have all kinds of different effects to inside that filter. Let's say an audio filter, like a guitar amp type filter, right? You can have it emulate all kinds of different guitar effects inside the FPGA DSP functions. So in that sense, FPGAs are an extension, the next step beyond CPLDs. Now, again, CPLDs, they're really ideal for a dedicated circuit. You're cleaning up a lot of logic on your board. You're making it nice and neat. It's still fast, and it can do a lot with 128 macrocells. But if you're going to go FPGAs, you're probably much more serious, and you're probably not even going to stop at CPLDs. You're just going to go right there, and you're designing stuff at a much higher level. So in this case, I just imagine DSP as basic starting point where you're going to be doing that. And you can imagine doing audio processing, video processing, all kinds of stuff. I mean, they do go very fast, gigahertz. So yeah, so FPGAs are in the same line except another couple orders of magnitude bigger.
Okay, great.
Awesome. Thank you so much. Those are all the questions I have for you today. So thank you, Bob and Dylan. And for the audience out there, if you have additional questions or comments, please email us at livestream@microchip.com after this broadcast. And don't forget to follow us on LinkedIn and subscribe to our YouTube channel. Back to you, Dana.
Thanks, Aaliyah. That's all the time we have for today, but excellent discussion, guys. Thank you so much for being here. If today's topic has sparked your interest and you'd like to learn more, I encourage you to visit our website at microchip.com, where you can dive deeper into the world of microchip technology. If you'd like more Coffee Break, head over to microchip.com/coffee break and click on the subscribe button to get updates for all things Coffee Break. You can also see upcoming episodes for Season 14. And of course, be sure to join us next time on Coffee Break as we explore AI ML development for Microchip microprocessors with Edge Impulse. That episode will live stream on Wednesday, November 6th. Until then, stay curious, stay creative, stay caffeinated.